zoax.net. Lesson 56, Bitwise Logical Operators. To follow along with this lesson, you will need to create a new console project and add a new file named main.cpp to it, as we did in Lesson 1. I explained logical operators in an earlier lesson. In this lesson, we will look at logical operators that operate on sets of bits. Where the prior lesson's logical operators focused on boolean values false and true, this lesson focuses on the bit values 0 and 1, which correspond to the logical boolean values false and true respectively. The logical operators from the previous lesson were AND, OR, and NOT, which I represented in C++ by the double ampersand, the double vertical lines, and the exclamation point. Recall that we had truth tables like this one that told us how each operator acted on each set of values. For bits and bitwise logical operators, we have a similar situation, except that we have one more operator, AND, OR, exclusive OR, and NOT. These are represented by a single ampersand, a single vertical line, a caret, and a tilde respectively. Like the logical operators, we can construct truth tables for each of the bitwise operators like this one for AND. These are the same as the logical operators except the exclusive OR, which is new. The truth table for exclusive OR is like the table for OR, except that when both values are 1, the result is 0. To illustrate, we begin with a simple program that contains the same print bits function that we have used before to output the 32 bits of an unsigned integer. In our main function, we initialize two integers with alternating bit values given as hexadecimal numbers. Recall that each f is 4 binary 1 bits, and 0 is 4 binary 0 bits. So p consists of 8 0 bits, followed by 8 1 bits, followed by 8 0 bits, followed by 8 1 bits, and q is 16 0 bits, followed by 16 1 bits. After printing these values, we output the values with each of the applied logical operators, OR, AND, exclusive OR, and NOT. Executing the program, we see the bit values corresponding to each of the logical operators. One interesting application of bitwise operators comes from bioinformatics, an area that I worked in for several years. DNA is composed of two strands that form a double helix, and each of the strands is composed of sequences of 4 bases that encode genetic information. These 4 bases are adenine, cytosine, guanine, and thymine, which are typically represented by the letters A, C, G, and T. Since there are only 4 letters, we can represent each one of them with a 2-bit encoding scheme. Here 00 is A, 01 is C, 10 is G, and 11 is T. It is well known that the bases A and T always chemically bond together on opposite strands. Likewise, C always bonds with G. These form the two sets of bonded base pairs. So if A is on one strand, T is on the other, and if C is on one strand, G is on the other. As I mentioned, we can encode each of these bases with 2 bits, and the base pairs, as I have designated them, are bitwise complements. This allows us to change from one strand to its complement by using a bitwise exclusive OR. To demonstrate, I have this simple program where I have assigned an unsigned int a set of 32 bits or 16 bases, according to our scheme. Below this, I have the complementary strand, which is generated by applying the exclusive OR to a sequence of 1s. Then the strand's portions are printed using a modified version of the print bits function that inserts a space between each base. Executing the program, we see the bases for the first DNA strand and its complement. The top strand encodes G, A, T, A, G, C, G, T, 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 C, 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 T, A, A. The bottom strand contains the corresponding complementary bases. Note that the bottom strand was generated by applying the exclusive OR. For simple black and white graphics, we can use bitwise logical operators to combine two graphics with OR, perform intersection detection with AND, create easy animation with exclusive OR, and negative graphics using NOT, our third program illustrates this. For this program, I have added a printAll function that outputs the bits of an array of 32-bit unsigned ints to print a large graphic like this horizontal bar. In the main function, we have 3 arrays of 24 unsigned ints, which are initialized with a horizontal bar, a vertical bar, and a blank set of all 0 bits. This third array will be used to store the result of our bitwise operations. Below this, we print the horizontal bar and the vertical bar. Then we create and print each of the bitwise logical operators on the result: OR, AND, exclusive OR, and NOT. Executing the program, we see each of the bitwise graphics printed as 0s and 1s. You will need to use the scroll bar to see the entire output, since each graphic takes up 24 lines. It starts with the horizontal bar and the vertical bar. After this, we have the OR, which combines the two to make a cross. The AND displays the intersecting square. The exclusive OR makes a cross with 0s in the intersecting region. And finally, NOT is the negative of the horizontal bar. We can use these operators to put graphics together. In the last program, I used the printAll function from the previous program to print graphics made of 0s and 1s again. At the start of the program, I have the horizontal and vertical bars again, which are combined here using OR and stored in the array called cross because they form a cross. The last array is called Christ because it holds a picture of Christ that looks like this. The last loop combines the cross with Christ using an exclusive OR and stores the result back in the cross array where it is printed as a crucifix. Executing the program, we see the horizontal bar, the vertical bar, the cross, which was a combination of those two using the OR operator, and finally we have the crucifix, which is created by applying the exclusive OR on the cross and the image of Christ. If we think about it for a minute, we could apply the exclusive OR to the crucifix and the image of Christ to get the cross back. This is how animations have sometimes been created, where a graphic is added and then removed, and then another is added and removed, and so on using the exclusive OR.